Well, that's fun. Um, I do have one question that I found out the homework
Hmm.
um to be a bit confusing at the moment,
Okay.
and I'm going to pull it up right now. It's a question about
Let me allow you to share screens. There's a thing I can do.
okay.
Uh, participants can share simultaneously, so now you can actually share your screen with me if you so desire.
Sure. Oh, that's nice. Let's try. Let's see here. Share. I want to share that one.
There you go.
Here
It's
we
coming
go.
up now.
Can you see the
Hmm.
homework screen?
Yep, I'm looking at it now.
Sweet. So I was going through it, and I haven't done much at the moment, but I was reading it. And this one, I don't know, it just caught me off guard a little bit. It says,
Hmm.
what below what temperature T does water shrink when heated?
Ah,
So I can see that the letter B and what I think it is to be density, but I'm not completely oh no, that's
that's the thermal coefficient of expansion.
oh, okay.
So
So that's
whenever
something
it's
completely different.
negative, that would tend to mean that an increase in temperature would actually cause it to contract as opposed to expand.
Okay. So that makes sense. Anything below then
Yeah,
I want
that
to
mark
say
right
like
there.
4.
Yep, and that happens to be exactly the 4 degrees that I hinted to you about. If you look at it, there's another place in your textbook where they do the density of water as a function of temperature, and it's a upside down parabola, a parabola opening down, and the peak of that parabola is at 4 degrees Celsius. And then there's another one where they do the density of water. That's in the book as well, and that's a parabola that's right side up. And of course, it has a minimal dense, or excuse me, a maximal density and a minimal pressure at 4 degrees Celsius.
Okay.
So,
Oh, yeah.
so yeah,
That
that's what
makes
you're supposed to
sense.
do. It looks like 4 degrees by that drawing, and you should be able to throw that in there.
And then here, let's go to the book because oh, I might not have. I don't have the book. I'll figure that out in a little bit.
Do you not?
Oops.
Did you buy access to the book electronically like that? I was curious to see if
So
anybody had any problems or if they had another way of buying books.
I was kind of lucky
Hmm.
where the homework that I have now, I didn't have to pay for it because it remembered my account
There you
from
go.
Physics 1.
Right.
And it just said, yeah, no, here's Physics 2 homework, but it came without the book.
That's cool.
Yeah.
So, do you need, if you need a copy of the book, you can stop by. I can loan you like my fourth edition or something. At least you'll have one, to read back and forth. Or I've got also several other authors that are just as good as Giancoli. It's just, it'd be nice to have the book. So let me know or just tell me you want to stop by and I can loan you a copy and just bring it back later.
Oh, yeah, I'll definitely hit you up on that. But
No
I
problem.
guess I gotta go. Class is about to start.
Yeah, that's the point. I guess we got to start up pretty soon. Looks like I got 5 people in here now. All right, I guess we should go ahead and get started. Nice talking to you, Alex, and Alex's girlfriend. Uh, Anybody have any questions before we get started? Remember, I'm going to jump in and just start teaching class probably every day because I'm a goober, just getting excited about stuff. So if you guys want to stop a second and say, "Hey, I got a homework question," try to remember to do that at the beginning of class because I'm going to forget 9 out of 10 times. But I remember this time. So anyone that's here have a question? Anahi or Giovanni or Nathan? I already talked to Alex about one of his questions.
I'm okay.
All right. All right. Well, I've got my iPad pulled up, and last time we have finished chapter 17, but to be honest with you, there was one little part I just didn't do because we were running out of time, but it's really simple, so I'm going to do that first, and then we're going to do a derivation that I just don't feel like it's good to offer the class the result without the derivation. So even though it takes some of the time, I'm going to go ahead and do the derivation as well. So let me go ahead and share my computer screen or my iPad screen with everyone. Now, this is in principle something that you can aspire to do on your own. And the more of these derivations that you can, more of these derivations that you can come up with, uh, the better off you are in terms of understanding the physics behind it and that sort of thing. So don't just assume when the author's doing derivations of equations that he's necessarily doing something that's intractable or unable to be understood. You guys can understand it. Now, they'll tell you, for instance, when they say it's beyond the scope, like I'm going to give you the Maxwell distribution today, and that derivation is a little bit lengthy, so we won't be doing that one, and your book doesn't even cover it. But the ones that your book covers is sort of the highest mark that you could sort of achieve if you're taking the class right now for the first time. So if you aspire to that, great. It'll pay dividends. But if you can't get it, that's pretty normal too. So first, I need to give you another version of the ideal gas law that involves a different measure of the amount of gas present. In the previous version, we used n, lowercase n, which is the number of moles, and the ideal gas constant R. However, in the new version, we'll use capital N, which is the total number of atoms slash molecules, and the Boltzmann constant. I haven't figured out how to put subscripts and superscripts in my typeset on my GoodNotes yet, so I just tried to make them small when I have notes like that. But I also have this wonderful problem in that now that I connected the keyboard to my iPad, every time I click on the screen, it sort of acts like it's wanting to type something. So we had PV equals nRT, and your author's using capital P and capital V. I usually use a lowercase p and a capital V. Uh, but that's neither here nor there. There's actually reasons behind it, having to deal with whether variables are extrinsic or intrinsic. So just keep that in mind. You'll probably learn that when you take thermodynamics, engineering thermodynamics, if y'all go for engineering. So, anyways, the ideal gas law we've been using is PV equals nRT, which in my high school class, our Mr. Williams just told us everybody remember pervert equals nerd. So. I guess that works okay. So whatever mnemonic works is great. Now, one way we can compute the number of moles is we can take the total number of atoms or molecules, which is big N, and divide it by Avogadro's number because Avogadro's number is the number of items in a mole of substance. So, for instance, if you have 1 mole of oxygen, then you have Avogadro's number of oxygen molecules. Remember O2, just like N2 and H2, they're naturally occurring in our atmosphere as O2, H2, N2, not just plain O, not just plain H, not just plain N. So in this case, it would be the 6.022 times 10 to the 23rd divided by the total number of atoms or molecules in the case of O2 or N2. Now, with that being said, we can then say PV is equal to capital N over NA, Avogadro's number, times R times T. But it turns out that that is a way of introducing a new constant because the fact that R over NA, which is again the ideal gas constant, 8.314 joules per mole Kelvin. So that's 8.314 joules per mole Kelvin divided by Avogadro's number, which is 6.022 times 10 to the 23rd, and that's reciprocal moles. So you write that as mole to the -1 power. You can put parentheses around it because it's a whole word. And when you do that, you're going to get 1.3806 times 10 to the -23rd. And now the units are just joules per Kelvin. And that is, in fact, another constant that we use in physics, and it's
Um,
called the Boltzmann constant.
sir,
Yes.
are we supposed to be seeing something on the screen?
Yes, that is weird. I'm not sure
Oh,
why
yeah.
my writing's not
Mhm.
showing. Huh. That is really weird. Okay, let me try unsharing and then resharing. I don't know why I've literally written a bunch of stuff on this page already. Well, not a bunch of stuff, but some stuff. Personal focus. Also, it today it made me sort of secure this GoodNotes program, so I should probably address that too because it's making me do a like a either a face recognition or a fingerprint recognition. I'm wondering if that might be some preference that's preventing you guys from seeing my changes on it. So let me see what happens now. Okay, it should pop up again. Thank you for letting me know. That's exactly the kind of feedback I need. Okay, so now it shows it, but I'm going to try to write something else and see if that shows. Okay, now it's showing. All right, I have no idea why that happened that way, but it clearly happened. So notice what I was saying is PV equals nRT. That's the leftmost equation here. And then I said N, the number in the ideal gas law, is the number of moles. And I said you could take the total number of molecules slash atoms, which is big N, and divide it by Avogadro's number, which is N sub A, and that would give you the number of moles. Because, like I said, a mole is 6.022 times 10 to the 23rd reciprocal moles or atoms or molecules or whatever. So when you divide the total number of atoms or molecules by the number of atoms or molecules in a mole, you get the number of moles. So I then wrote this new value of N. I wrote it in, I don't know why it's doing this. I wrote it in this form, which was really supposed to be, I don't know why this little text thing keeps popping up, but it's obviously making a pain in my butt, and I don't know why that's there. Must have typed a period in by mistake. Let's say delete. Okay. So you can see I replaced the lowercase n with capital N over n sub a, but now I'm going to take the n sub a and put it under the r. And when I do that, you get r over n sub a is equal to 8.314 joules per mole Kelvin divided by 6.02 times 10 to the 23rd. Just going off the top of my head, that was the number that I wrote down for it, 1.3806. So let me double check. 8.314 divided by 6.022 times 10 to the 23rd gives me 1.3806 times 10 to the negative 23rd joules per Kelvin. And as I said, this is Boltzmann constant. So you sometimes just write it with K. I notice your book is mostly writing it with just the lowercase k. I often instinctively put a capital B just to remind us it's Boltzmann constant. Okay, so now when we do this, we have a new version of the ideal gas law, specifically PV equals N K T. Okay, so that's a new version, and that's what we're going to use in the derivation to come. So let me go ahead and move on with that. Make sure also that I'm not misremembering or forgetting to do anything in particular. So this chapter, before we get started, is called the Kinetic Theory of Gases, and it has, as always, a chapter opening question, specifically the typical speed of an air molecule at room temperature 20 degrees Celsius is what? And the answers are nearly at rest, meaning less than 10 kilometers per hour, on the order of 10 kilometers per hour, on the order of 100 kilometers per hour, or on the order of 1,000 kilometers per hour, or C, near the speed of light. Okay, so that's the kind of question that you should take a poke at, just because the actual act of thinking through something makes it embed in your head a little bit more. And then when you pose an answer, that helps you further. And then when you get feedback that allows you to figure out whether your answer is right or wrong, that is yet another opportunity for you to commit the thing to memory. So your ideal scenario is you read this, you guess an answer, and don't feel bad one iota about being wrong unless you just guessed at random instead of putting any thought into it. Okay. So do that, and we'll get pretty quickly there. So what we're going to do is apply something called kinetic theory, and it's part of, or I always picture it as part of statistical mechanics, and it's a very powerful tool. Specifically, statistical mechanics along with kinetic theory can make up, for instance, the Maxwell distribution, which we'll learn about today. So now I'm going to turn to the next section. That is just sort of the opening part. And the next section is 18.1, the ideal gas law and the molecular interpretation of temperatures. And it says, now applying the four assumptions listed on page 18 of your text, assumptions that define the properties of an ideal gas within the kinetic theory model, I will derive an equation for the pressure on the walls of a container holding n atoms/molecules of an ideal gas at absolute temperature T. The real gas behaves closer to an ideal gas when this real gas is at low pressure and far from liquefaction point. So that's just an underlying principle that you need to understand about ideal gases. If you're dealing with low pressures and not close to a change of state, then you get an ideal gas law acting just like the real gas does. The assumptions we're doing are there are a large number of molecules, capital N, each of mass lowercase m, moving in random directions with a variety of speeds. This assumption agrees with our observation that a gas fills its container. And in the case of air on Earth is kept from escaping only by the forces of gravity. So what we're seeing here is we're saying, hey, any sample of gas has a very distinct number of molecules, and those molecules, and again, I always use the phrase atoms/molecules. I'm going to try to just not say slash every time. I'm just going to say either atoms or molecules. But no, every time I mean atoms or molecules, whether I use the word atoms or whether I use the word molecules. But by assuming that they all have a mass m and they're all moving at a range of speeds, then you might get the idea that, for instance, the gas could escape from the Earth, and it could if its velocity was, i.e., the escape velocity of the Earth, which we learned about in chapter 6. Part two, the second assumption is the molecules are, on average, far apart from one another. That is, their average separation is much greater than the diameter of each molecule. So remember when we did a solid, we found that basically in a lattice, the copper atoms are on the order of 10 to the negative 10th meters apart. And I also mentioned to you that we can also treat that as roughly the diameter of the atoms. And then I said under the atomic hypothesis that those molecules in the solid state are vibrating in place in specific lattices. Whereas in the liquid state, they're vibrating, but they're also sort of moving, rolling all over each other. In some sense, because they're still rather close to each other, there's an attraction between each molecule and its nearest neighbor. And that molecule and its nearest neighbor is going to be held together for an extended period of time on the microscopic level. But if you looked at it at average time, you wouldn't find one molecule being paired up with another molecule twice at the ends of a second. So, but we'd expect it to apparently not be that held to the nearest neighbor, but it will be on a small order of time. Part three, the molecules are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Although molecules exert weak attractive forces on each other between collisions, the potential energy associated with these forces is small compared to the kinetic energy. So we're ignoring the idea that two atoms, when they get close to each other, we know what happens. The electrons of the atoms are kind of repelled by the other electrons of the atoms, and therefore one atom will more comprehensively push the electrons to the opposite side of its body than the other one does, and therefore that half of the atom will look more positive and be attracted to the other electrons of the atom. What we're saying is that force is really small compared to, well, I should say the energy, the potential energy associated with that force is rather small compared to the kinetic energy of the molecules. So we're going to ignore that. And not only that, the fact that they're so far apart means that they're going to interact like that for a very small fraction of their time. And then finally, collisions with another molecule or the wall of the vessel are assumed to be perfectly elastic. Remember, that means kinetic energy is conserved. Like the collisions of perfectly elastic billiard balls, we assume the collisions are very short duration compared to the time between collisions. Then we can ignore the potential energy associated with the collisions in comparison to the kinetic energy between collisions. So that's what the assumptions we're going to use are, obviously I didn't take time to write that out, but now I'm going to go ahead and draw a coordinate system and give you an idea of our system and what I'm trying to point out here. So what we're going to say is this is our x-axis, this will be our y-axis, and this will be our z-axis. You might notice that this is a right-handed coordinate system. If you hold your right hand up, put your index finger straight out like you're making, a gun made out of a hand, like you did when you were a kid, pow, 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 right? And then you bend your other finger maybe at 90 degrees, but it can really be just about any angle for when we do cross products. But right now, I'm just going to do it like this. And if your index finger is the x-axis and your middle finger is the y-axis, then you have no choice but to point the z-axis in the direction of my right thumb. If you ever set up a coordinate system that's not right-handed, you need to erase it and fix it because it's going to become a problem, and it's a pain in the butt to deal with. So just always make right-handed coordinate systems. That'll be a lot easier. Now, in addition to this coordinate system, we're going to imagine that we have a box and that box has very specific dimensions, which we're going to make use of in a second. I'm going to say this end of the box has an area A, and I'm also going to say that the other end of the box is a very specific distance away, and that specific distance is lowercase l. Okay. Now in that box we have some gas, and that means you're going to have a bunch of little molecules running all over the place. But what we're going to think about right now is a single molecule that of course has a velocity that's in the x direction, the y direction, and the z direction. But all we're caring about right now is the little x component. Okay. Now, what's going to happen is this molecule is going to move, bounce off this wall, and then elastically collide off of it and travel off in this direction with a new velocity. And again, what I'm saying is the component of velocity that's parallel to the x-axis is v sub x, and the component of the velocity here is v sub x as well, but it's pointing in the opposite direction. So I'll call it negative v sub x, and the mass is just plain m. So my goal here is to model this gas like a gas and see if I can make sense of, for instance, pressure and volume and all that sort of stuff. In fact, you can sort of picture it as a derivation of the ideal gas law, or if you assume that you know the ideal gas law, then it's a derivation of the relationship between temperature and kinetic energy of the molecules. Okay. So what our claim is within this model of kinetic theory is there's going to be, n, which is on the order of 10 to the 25th or even higher molecules. And those molecules bouncing off the left-hand side, basically, even though they're sporadic and stuff like that, there's so many of them that you don't notice any kind of fluctuations in the pressure, but they are in fact responsible for the pressure. So what we're going to use is Newton's second law in the form that he originally wrote it, which was F is equal to dP dt. So we're going to make the argument that the force on the left-hand plate face is given by the change in momentum by the change in divided by the change in time. So we're going to say this is approximately equal to delta P over delta T, and I'm going to focus just on one-dimensional motion. So I'm ignoring the fact that the y components are going to do some stuff and the z components of velocities are going to do some stuff. I'm just thinking about the x components, because the y component, for instance, if the mass had a y component, it would just bounce off that left wall with no change in the y component because of its conservation of kinetic energy, which is a result of elastic collisions. So the y components don't matter, and the z component does the same thing. It's going to tend to make it, continue to move on in the same z direction with the same v sub z. Okay, so v sub x is what we're focusing on. V sub y is not going to change, and v sub z is not going to change, just as a result of it hitting the left face. So I can go ahead and calculate what the change in momentum is. The change in momentum is supposed to be P final minus P initial. And if you notice, I drew the initial velocity as going in the negative x direction, and the final velocity is going in the positive x direction. So we're going to use basically the fact that the momentum after, since kinetic energy, or excuse me, kinetic energy before, so kinetic energy initial equals kinetic energy final, means that 1/2 mvx squared is equal to 1/2 mvx final squared. And that's where I get, since the mass didn't change and the 2 didn't change, clearly the magnitude of Vx can't change. So that's why I was able to make the conclusion that if the velocity before it hits the wall is positive V sub x, then the x component of velocity after it hits the wall will be negative V sub x. It's all because of that kinetic energy formula. So now I'm going to plug that in. What I'm going to get is m v sub x minus negative m v sub x, which gives me 2m v sub x as the change in momentum. Everybody follow that? Now, what's going to happen is that molecule is going to bounce off the left-hand wall, and depending on how close it is to the top wall or the bottom wall or the front wall or the back wall, it might actually bounce into one of those other 4 walls, okay? But that's not going to change anything. It's just going to change the direction of the y component of velocity, for instance, if it hits the top wall or the bottom wall, or it's going to change the direction of the z component of velocity if it hits the front wall or the back wall, but it's going to totally not affect the x component. So what's going to happen is that thing's going to hit the left wall and then come off this way. Maybe it bounces off this wall too, but that doesn't matter because the x component of velocity is going to stay the same, and then it's going to bounce off this wall and then come back and bounce off the other wall again. So with that in mind, you realize that multiple collisions with the left-hand wall for this one molecule is responsible for the pressure. So in order for us to figure out basically how much force it is, I need not only a change in momentum, but how much time it takes between those individual collisions that change momentum. So realizing that the mass m is going to move a distance L to get to the right-hand wall, and then another distance L to get back to the left-hand wall, then that tells me, since velocity is equal to change in distance divided by change in time, that tells us the time between adjacent collisions, or consecutive collisions, not adjacent, but the time between consecutive collisions is going to be the change in position, which is going to be a length of 2L, because again, it's going to go from the left wall, which we just calculated, to the right wall, and then from that right wall back to the left wall. So it's going a total distance of 2L, and it's going to, in fact, be 2L divided by V sub x. So now I can say that on average, the force on average is delta P over delta T, which gives me 2m V sub x divided by, now I'm going to divide by the delta T, which is 2L V sub x. Now, when you divide a fraction by a fraction, that's the same thing as multiplying by the reciprocal of that fraction down there. So I'm flipping over the 2L over Vx, and you can see immediately that the 2's are going to cancel out, but we're ultimately going to get, in fact, m Vx squared over L. Okay, so that's the force that one molecule is going to put on the wall on average during a time delta t. Okay. Now, with that in mind, we might want to think, well, wait a second, it's not just M, it's not just one mass M that's doing it, it's actually N of those things. So in fact, the total pressure due to all the molecules is going to be basically the pressure that or the force that we just calculated for each of the individual molecules. Well, that force is a mass m times Vx squared divided by length L. But notice the length L and the mass m doesn't change from one atom to the next. So it's now going to be, I don't know who's, it's now going to be m over L, and then it's going to be Vx sub 1 squared plus Vx sub 2 squared plus dot 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 plus on up to Vx sub n squared, where we've just taken the liberty of like imagining we're painting little numbers on the atoms so we can keep track of them. So the first atom we did, or the first molecule we did, had the number 1 on it, but we've got capital N of those molecules, so that's why I had to add all those up. Now, you might think that hasn't brought us any closer, but it actually has, because we can figure out exactly what the average is by computing the average of both sides of this equation. So if I take the average of F total, and that's supposed to be a bar. I almost drew an arrow there, but the bar over top of it's a way we indicate average. Another way we indicate average is sometimes we put less than and greater than symbols around it. So just be in mind, keep that in mind. That's two ways we specify an average, is either by putting a bar over it or putting those little less than symbols and then greater than symbols around it, like parentheses. So with that in mind, let me tell you that F total is going to be, in some sense, the related to the average of all these. So if we look, F total is what we're going for. So if we look, we might realize that the average of the square of the velocities is something kind of important. So this is the average of the square of the velocities. I'm calling it v sub x squared with a bar over it. And the way you compute the average of a square is you take vx1, which is one of the quantities, and you square it. And then you take vx2, which is another one of the quantities, and you square it. And you keep on doing that until you get to the very last one, which is Vx sub n squared. And then, of course, to make it an average, you'd have to divide by the total number of quantities that you put in. So you're dividing it by n. Okay? So that means the average velocity can be found by taking or the average square can be found by taking the sum of these Vx's divided by n. With that in mind, then we can go ahead and say that F total on average is going to be M over L. Now, if I take this quantity right here and I multiply both sides by n, then I'll get just this quantity. Okay. In other words, if I multiply both sides by n, on this side, I'm only going to have this, and this is exactly the same thing as that. So all I have to do now is replace this with this times n. And that's what I'm going to do. I'm going to say this is n. Let's get my pen back. This is going to be n times v sub x squared with a bar over it. Now we're almost there, but we got to do a little bit more. So, for instance, what we have to do is we need to think about, I don't want, and I can't necessarily do as easily an experiment to determine the x component of velocities of the individual molecules of a gas, right? It would be hard enough just to figure out what the average velocity is, much less the x component or the y component or the z component. But with that thought, I can use something else. It turns out that the square of the velocity for a particular molecule or atom is given by the sum of the squares, Vx squared plus Vy squared plus Vz squared. And that's just our Pythagorean theorem, right? The sum of the squares, if they're all three perpendicular to one another, is equal to the square of the magnitude. So that's what we've done there. Now, there's no reason to assume that x direction is particularly important, nor the y direction, nor the z direction. So just on a statistical basis, we can make the conclusion that it seems unreasonable for Vx on average to be different than Vy squared on average, or to be different from Vz squared on average. And I should have said V squared, Vx squared. So we can also use our understanding of statistics to say that the average of the square of the x velocity is equal to the average of the square of the y component of velocity, and that's equal to the average of the square of the z component of velocity. So what I'm going to do is replace all these other ones with vx squared. So that's going to be vx squared plus vx squared plus vx squared, and therefore we get 3vx squared. And finally, this tells us that v squared bar is actually equal to uh, 3 vx square barred, like that. So I can also say now that we can replace the vx squared with 3 times v squared, or excuse me, 1/3 times v squared. So with that in mind, I'm going to plug this result into the f total we had. So the f total we now have is f total on average is equal to m over L times n. Now, in place of Vx squared, I'm going to replace that with V squared bar divided by 3. Now, again, we're almost there. The difference between pressure and force is pressure is force divided by area. And as we saw, the area on the left-hand face is A. So I can now say that P total on average is equal to F total on average divided by A. So that gives me M times N times V squared average divided by 3 times A times L. But can anybody tell me what A times L is in terms of this diagram? And just in case anybody might be typing it in the chat, I'm going to make sure I can see the chat. Y'all should go ahead and chat me your first and last name if you haven't already. It looks like someone did. And Alex is right, it's volume. So now what we can say is this is 1/3 times M times N times the average of the square of the velocities divided by the volume. So that almost brings us there. We now have pressure on average is equal to, or let's actually go ahead and not take this step. Let's go ahead and take the velocity. Well, I'll copy this over. That'll make it a little easier. So let me do this. I'm going to copy this quantity over to the next page. Oops. Copy. Now I'm going to paste it here. And this is the result we've got. So now I'm going to pull the V to the left-hand side, and what I'm going to get is P times V is equal to 1/3 times N times M V squared bar. Okay, now that looks like kinetic energy, and that's really what I'm shooting for. So if I multiply by 2 and multiply by 1/2 at the same time, then I'm just multiplying by 1, so that's okay. So that's what I'm going to do. I'm going to go ahead and say this is 2 over 3 n times 1 over 2 mv squared bar. And you see that this in the parentheses is in some sense the average kinetic energy. That's the K bar. Okay. And that really is what we're trying to do here. So now that I have that part, we're in a really good spot. Now I'm going to go ahead and use the fact that pressure times volume is equal to N times the Boltzmann constant times T. So that if I went ahead and solved for PV over N, I would get PV over N is equal to 2/3 times 1/2 m v squared with a bar over it. So that's my PV over N. But that PV over N is also equal to K times T. So now I can say K times T is equal to 2/3 times 1/2 mv squared bar. Or finally, the big result that I wanted is the average kinetic energy K, which again is that quantity in parentheses. That's going to be 3/2 K times T. And of course, that's also equal to 1/2 m v squared bar. And in fact, there's a quantity called the root mean square speed, VRMS, which basically says, okay, you take the square of a quantity and you average that, which is what we have with the V squared with a bar over it. And then you divide it by, or once you've averaged that, then you can take that quantity, the V squared, and take the square root of it, and it'll have the same units that velocity has. So it's more like a velocity. That is what we call the root mean square velocity. So if you take the average of the square of the velocity and then take the square root of that, you get the root mean square velocity. So I'll just write that off to the side. That's going to come in handy. VRMS is equal to the square root of the root mean of the square of the, or excuse me, of the average of the square. Okay. So this is our big expression, and one way of thinking about this is what I've written down here. This result can be interpreted as the modern definition of temperature. It says the absolute temperature of an ideal gas is directly proportional to the average translational kinetic energy of the atoms slash molecules of that ideal gas. Therefore, the random motion of the atoms molecules is called thermal motion. Okay, so the actual definition in some sense of what temperature is. So if you say something has a temperature of, 12 Kelvin, for instance, what that means is I can use that 12 Kelvin and figure out exactly what the kinetic energy of translational motion the atoms slash molecules have. Okay. Now, translational means the whole atom or molecule moving left and right. That might be one dimension. In, out, that's another dimension. And up, down's the third dimension. Those are the translational velocities. There's other motion that they have. For instance, in the case of a diatomic molecule like oxygen O2 or nitrogen N2 or hydrogen H2, you have two atoms more or less acting like they're connected to each other via a spring, so they're bouncing back and forth like this while they're moving left, moving forward and backwards, and moving up and down. Those moving left and right, moving up and down, moving in and out, that's all translational motion. This is totally unrelated. That is not part of what the temperature is. So the kinetic energy associated with this has nothing to do with the temperature. The kinetic energy associated with orbiting this way has nothing to do with the temperature. The kinetic energy associated with them rotating like that has nothing to do with the temperature, and the kinetic energy associated with them rotating this way, which is really really small in immeasurable, basically, that's not relevant to the temperature as well. It's only the translational motion that matters in determining the temperature. So, everybody follow the equation that I just got? Anybody have any questions on that? All right, now we're in a place where we can go ahead and do some problems with that. So I've written up a couple of examples. These are very much like the ones in the book. Some cases I've changed the numbers. I've changed the wording on all of them because I'm trying not to violate copyright. I'm not sure a judge would agree that I'm not violating copyright, but I hope so. Anyways, compute the average kinetic energy of molecules of an ideal gas at 20 degrees Celsius. Again, I can't write subscripts or superscripts, so it was really hard for me to write a degree symbol, so I just wrote degrees. With that in mind, let's compute the average kinetic energy of molecules. So according to our equation, the solution can be gotten by applying the average kinetic energy equals 3/2 kT. Now, in this case, I'm not trying to find the velocities or anything. I'm actually trying to just figure out the kinetic energy. So I don't need to interpret the average kinetic energy as 1/2 mv squared bar. In this case, I'm just trying to figure out what K is. So now I can go ahead and do that. I'm going to say the average kinetic energy is 3/2, which is 1.5, times the Boltzmann constant, which is 1.3806. Now, that's just habit. I memorized a long time ago the Boltzmann constant, and actually I memorized it as 1.3807. That's what I've had in my head forever. But most recent results show that it's actually a 6 in that digit. So anyways, 1.3806 times 10 to the negative 23rd joules per Kelvin. And the reason why I was saying that is, I only gave you 3 sig figs with 20.0 degrees, so you could just call it 1.38. That would be fine. I would really like you always to go one digit beyond the sig figs that you're using. That way, you don't accidentally over round. So it might be decent for us to call this 1.381. That would be a little better than 1.38, but either one's acceptable. I'm not going to take off points.
I have a really quick question.
Yes.
Are we going to be given that number anywhere in all of the given number sheets or anything?
Yes. If you look in my helpful documents and links, you'll see the allowed equation sheet, and that has some constants on it. But more specifically, you'll see a bunch of photographs from the inside cover of the textbook. Those are all given to you as well. When you take your first practice test, not the practice chapters, but your actual practice test, you'll see exactly what constants come with it, and that's one of them.
Okay, thank you.
No problem. So now when I do this, I have to take 3/2, which as I told you is 1.5. So I'm going to say 1.5 times 1.3806 times 10 to the negative 23 times. Now remember, the absolute temperature is the Celsius temperature plus 273.15. So I have 293.15. So I'm going to multiply this by 293.15, and this gives me 6.071 times 10 to the negative 21. And of course, the units come out in joules because you can see the 293.15, I didn't write the unit on it, I am now, is in Kelvin. So that Kelvin cancels out with this Kelvin, leaving joules. Now, that number is not that helpful to us. We can't immediately see whether that's a big quantity or not, but just to give you an idea what it is, we can consider 1 mole of this gas and say, calculate how much kinetic energy that is. For 1 mole of gas, this kinetic energy is, what I'm going to do is take the 6.071 times 10 to the negative 21 joules, and I'm going to multiply that by Avogadro's number, which is 6.022 times 10 to the 23rd reciprocal moles. And when I do that, I get 3,656. Now, if you thought about given this much kinetic energy, the kinetic energy associated with 1 mole of this gas, if you considered giving a 1 kilogram object this much kinetic energy, it would actually be traveling around 85.4 meters per second. And the way you can do that is you can say 1/2 times 1 kilogram times v squared is equal to 3656 joules per mole. And that would give you V is on the order of 85.48 meters per second. So that is a lot of kinetic energy associated with 1 mole of an ideal gas. And remember, a mole of an ideal gas fits in 22.4 liters at standard temperature and pressure. So that's just 22.4 liters of air, for instance, would have as much kinetic energy as a 1 kilogram object traveling at basically 86 meters per second, which is, on the order of hundreds of miles per hour, basically. Over 100. I think it was 160 or something like that. Anybody have any questions on that one? All right, now let's try another calculation. This one says calculate the root mean square speed of the molecules of oxygen and nitrogen at 20 degrees Celsius. So I'm sticking with the same temperature I did before, but this time I want to calculate the velocity, the root mean square velocities of these molecules. So for starters, I need a slightly different equation. I mean that equation, but I need 3/2 kT is equal to k bar, but instead of k bar, which is the average kinetic energy, I'm going to put it in terms of the average kinetic energy, which is 1/2 mv squared with a bar over it, and that means v squared with a bar over it is equal to notice the 1/2s cancel from both sides, so this cancels out with that, and I'm going to get this quantity being 3 kT over m. Oops, need to go back to my purple. This is going to be 3 kT over m. Therefore, VRMS is equal to the square root of v squared bar, which equals the square root of 3 kT over m. So that's a formula we're going to use repeatedly. It's basically about 1.73 times the square root of kT over m. And in order to do that, though, I need the mass of the individual molecule. So for O2, I need the mass of O2. And of course, the mass of O2 is given by, if you look at the periodic table, it's like 7.9963 or something like that for oxygen. And I actually have to use 2 oxygens. So that's going to be essentially, instead of being approximately 8, it's going to be approximately 16. So I'm going to say 16 unified atomic mass units times 1.6605 times 10 to the negative 27th kilograms per unified atomic mass unit, and that's going to give me an individual mass of 16 times 1.6605 times 10 to the negative 27. That gives me a mass of 2.6568 times 10 to the negative 28th. 0.6605 times 10 to the negative 27. Oh, sorry. Misread that. I was looking at it. Notice it said I wrote 28, but that's just my old person vision. My calculator says 26. So at least I was paying close enough attention to realize that when you multiply a number 10 to the negative 27th by 16, it should get bigger, not smaller. So luckily that fixed it. So it's 10 to the negative 26 kilograms. Now, I need to do the same thing for nitrogen, but I'm going to show you a neat little trick that will allow me not to even use it. But the mass of N2 is 14U. That one turns out to be like 7.01, and then of course it's N2, so it's got to be like 14. And we again do that, but I don't really need to do this. Okay, I'm not going to need to do it. I'm going to show you why in a second. So now I'm going to take the root mean square. By the way, I normally abbreviate this capital RMS as opposed to lowercase. So you'll see me do that a lot, even though your book uses lowercase. So for O2, I'm going to say this is the square root of 3 times 1.3806. Again, you can feel free to use 1.38 or 1.381 times 10 to the negative 23rd joules per Kelvin times the temperature, which is 293.15 Kelvin. All that's going to be divided by 2.6568, which really should only be 2 sig figs. So to be honest with you, none of those are sig figs. Times 10 to the negative 26 kilograms. And you should take the time to convince yourself that all this stuff cancels out to leave meters squared per second squared under the square root. And then, of course, when you take the square root of it, you get meters per second. But you guys should convince yourself of that. So I'm going to do 3 times 1.6, or excuse me, 1.3806 times 10 to the negative 23 times 293.15. And now I'm going to divide that by 2.6568 times 10 to the negative 26. And that gives me 4.570 times 10 to the 5th meters squared per second squared under a square root. So now I'm going to take the square root of that by raising it to the 0.5 power. And that gives me, I think, the same thing I got last time. Last time I got 687. This time I'm getting 676. I guess that's pretty close. It might be a difference of me. I might have used more sig figs or less sig figs or something like that. But anyways, this is what I get for this. Anybody else confirm this calculation? So this is VRMS for O2. And by the way, it's on the order of 1,500 miles per hour. So now you have an idea what the answer to the opening question is. Okay. Now we need to do the exact same thing for nitrogen, but like I said, I promised you there's a trick we can do to make it a little easier. What I can do is say V root mean square N2 is equal to square root of 3kt over m N2. And actually I should put that 2 as a subscript there. Now, this is the same thing as the square root of 3kt over m O2, as long as I multiply by the mass of O2 divided by the mass of N2. Okay? So this quantity right here under the square root, that's the actual velocity of the O2. So all I have to do now is write 676 meters per second times the square root of, now remember we have a common factor of conversion 1.6605, but I don't need to write that. I can just write 16 over 14. So now I'm going to take my 676 and multiply it by the square root of 16 divided by 14. And that gives me 722 meters per second. And remember, we only had 2 sig figs, so that's all that is. So that's the root mean square velocity of M2. again at 20 degrees Celsius. Now that one happens to be roughly 1,600 miles per hour. So hopefully you can tell that obviously the less heavy the individual molecule is, the faster it'll go. So with that in mind, if you're thinking about escape velocities and the evolution of a planet, for instance, in terms of astronomy, then what you figure out is that obviously the lighter mass molecules are less likely to stick around. And two of the very lightest gases that exist are hydrogen, the lightest, and helium, the second lightest. So you'd expect that because of our sun being made mostly of hydrogen and helium, that the atmosphere of the Earth would initially be made of mostly hydrogen and helium. But because their masses are so low, their average speeds due to thermal motion are very, very fast. And the rule is that we use in astronomy is if the escape velocity is 6 times or less, or excuse me, 6 times or more than the average thermal velocity, then it's going to disappear. And it turns out that hydrogen and helium have basically an escape velocity that's less than 6 times their thermal velocity for the origins of the Earth. Anybody have any questions on that?
Why did we use 16 as the mass of O2 when in the first velocity equation we used the calculation that we got for kilograms?
Uh, because basically the difference is for the calculation that I did right here, that is 16 times this. When I do it down here, that would be 14 times this, but you can see by taking MO2 and divide it by M into, this quantity is going to cancel out, and I'm just left with 16 over 14. It was just a quick way. You don't have to do that at all. I'm just telling you that's a way you can save some work if I have to ask you to do two different calculations. Do you understand now why it's 16 and 14?
Yes, thank you.
No problem. Anybody else have any questions? All right. So let's press on. Now, compute the average of the digits 1 through 6, and then compute the root mean square average of the digits 1 through 6. Assume they are good to 3 sig figs. So this is a question where I want you to understand the difference between a root mean square velocity and just an average velocity. So let's start off with the average of the first 6 digits. So I'm going to say d bar is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Now that's 6 different numbers, so I got to divide it by 6 to get the average. And 1 plus 2 is 3, plus 3 again is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. So I get 21 over 6. I know that 6 goes into 18 3 times. That leaves me 3 left over. So this is 3.50. So that's what the average of the first 6 digits is, 3.50. If these were velocities, for instance, the average velocity would be 3.5 meters per second. Now I'm going to compute the root mean square of the digits. Okay, the way I'm going to do that is I've got to take the square root of all this, but instead of adding up 1 2 3 4 5 6, I'm going to add up 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, and I'm going to divide all that again by 6. Now, 1 squared is 1, plus 2 squared is 4, so that's 5, plus 3 squared is 9, 9 plus 5 is 14, plus 4 squared is 16, 16 and 14 gives me 30, 5 squared is 25, so 30 and 25 gives me 55, and then 6 squared is 36, so that gives me 91. So I've got 91 over 6 square root. I happen to know that 6 goes into 90 15 times, and that would leave 1 left over. So this is the square root of 15.166 on forever. And when I take that square root Hopefully y'all are following me on all these calculations so you can check any arithmetic errors. But this gives me 3.89. Well, it doesn't give me meters per second because these weren't given as meters per second. But if it was a velocity, it'd be given as meters per second. Anybody have any questions here? So that's an important thing. That's something we need to understand is the difference between the root mean square velocity and the average velocity. This will come in handy, for instance, when we start talking about AC electricity. Specifically, AC electricity is given by V0 times sine omega t, which means it's going to oscillate back and forth. If you tried to take the average of that over one cycle, you'd get zero because the sine wave is exactly the same amount of area above the curve as there is below or above the axis as there is below the axis. So when you go over one cycle, you've got a positive area and a negative area that are equal. Therefore, they add together to give you zero. So the average of the velocity when it's AC is not a helpful quantity. In fact, they tend to use the root mean square. And if you ever heard anybody talk about our electricity is 120 volts or 125 volts, they're meaning the root mean square voltage, not the average voltage, and not the peak. The peak is actually a square root of 2 times that, so it's like almost 180 volts is really what the peak is, and it goes all the way up to like 180, 178, something like that, and then all the way back down to negative 178, and all the way back up to positive 178. Any questions on that? All right. So, though these calculations give experimentally verifiable root mean square speeds of the atoms, molecules of ideal gases, it would be even more helpful to determine how the speeds of atoms and molecules within the gas are distributed. James Clerk Maxwell, who we're going to spend a lot of time studying once we get to chapter 21, used statistics to compute this distribution in 1859. His result was this. Basically, what he found was that F of V, which is a probability density. Okay, I'm going to explain that in a second. But f of v turned out to be 4 times pi times n multiplied by the mass m of the individual molecule divided by 2 pi times k times t. And this whole quantity is raised to the 3/2 power, and then this is multiplied by the square of the velocity times e to the negative mv squared over 2kt. Now, what this means is f of v dv is the number of atoms slash molecules with speeds between f of v and f of v plus dv. Okay, so that's what that is. And in order to make some use of that, we need to understand a little bit about calculus-based statistics. So, for instance, if I wanted to calculate the total number of atoms or molecules, the total number n would be the integral from 0 to infinity of f of v dv. And you can verify that on your own if you want. But it's worthwhile doing. You can see the n pops up in there. Another thing that might be handy is the average velocity. And when you're actually using calculus to determine the average velocity or average anything, you multiply the thing that you're trying to find the average of by the probability density. So in this case, we would multiply by v times f of v dv and then integrate from 0 to infinity. Similarly, if we wanted the average of the square of velocities, we would take and multiply, or we would take and integrate from 0 to infinity of v squared f of v dv. So those are things we just expect you to know. Now that I've told you that we expect you to know them, I've never put these on the equation sheet, and occasionally I do one of these questions. So I would say you just need to learn this just to be an educated person who's going into engineering or any of the sciences. Okay, so just in terms of probability, you have to know that the probability density times the variable integrated gives you the average. The probability density times the square of a quantity gives you the average of the square, times the cube of the quantity gives the average of the cube, so on and so forth. Now, with that in mind, it says use the Maxwell distribution to derive a formula for A, the average speed, that's the V bar we were talking about, and B, the most probable speed of atoms, molecules of an ideal gas at temperature T. So let's start off with part A. I'm going to go with green this time. Let's say solution. F of V is 4 pi n. The 4 pi n formula, by the way, is included in your book, in your equation sheet, times m over 2 pi kt to the 3 halves power times v squared e to the negative mv squared over kt, and v bar is equal to the integral v f of v dv from 0 to infinity. So that's what we're going to do. The other thing we're going to do is find the most probable speed, and I'll say the most probable speed is found by v bar implies df over dv set equal to 0 and solve for v. Okay, so that's how we're going to do part B. Oh, excuse me, I wrote a bar over that. That's not supposed to be a bar over it. Your book is subscripting that with a P. So I'll say V sub P, meaning most probable. Okay, so to calculate the most probable, we're going to take the derivative of the Maxwell distribution and set that equal to 0 and then solve for it. This other one's actually a little tricky, but you get to use something kind of neat. Specifically, we use the integral of uv equals the equals uv minus the integral of v du, integration by parts. So let me show you how we do it. Here's part A. V bar is equal to 4 times pi times n times m over 2 pi kt to the 3 halves. Notice I just pulled all that out in front of the integral. Now I'm integrating from 0 to infinity of v cubed, because it already had a v squared in it, so now it's v cubed times e to the negative mv squared over 2 kt dv. Now, what I'm going to use is the integral, and I'll write it in different terms of different symbols. The integration by parts, I normally write it as the integral of u dv, but we have a v in there, so that causes problems. So I'm going to say the integral of u d omega is equal to u times omega minus the integral of omega du. Now, the trick with using this is a part where the words I say are way more important than the things I'm getting ready to write down. So you might want to take time to write this in sentence form somewhere. But when you use integration by parts, the trick is often to use dw, or d omega in this case, as the quantity that is easily integrated, and then the u is a quantity that would be difficult to integrate, and this allows you a way of getting around that. So what I'm going to do is I'm going to say let's let u, well, let's start off with the part where I told you the d omega should be the part that's easy to integrate. So what I'm going to say is I'm going to let d omega equal v times e to the negative mv squared over 2kt, like that. And then that would mean that omega is equal to the integral of v e to the negative mv squared over 2kt dv. Now I've already taken out the v and the e to the negative, so I also need the u, and the u is going to be v squared, which implies du is equal to 2v dv. So that's how we go about using this integration by parts. So what I'm going to do now is try to compute those integrals so you'll know exactly what to do. So the integral of omega du, which is partly what we have to do, I should say just plain omega is going to be equal to v times e to the negative mv squared over 2kt dv. I'm going to let x equal mv squared over 2kt, then dx is going to be mv over kt dv. Notice I took the derivative with respect to v. That made it 2mv, but then the 2 in the denominator canceled it out. So now I can say this is going to be equal to, I'm going to replace the dv with kt over mv. So I'm going to say integral kt over mv times the v that was already there times e to the negative x. And now that I've used the kt over mv, the kt over mv times the existing dv is in fact the dx. So now I can go ahead and put the dx here. Now notice the v's actually cancel out by doing this, and we just got the integral of e to the negative x, which is super easy. It ends up becoming e to the negative x, but we have times kt over m times e to the negative m. Now I'm replacing the x with mv squared over 2kt. So that's what that is. And then I'm supposed to, of course, just use that. It would be plus a constant, but that's the actual omega that I have in my integration by parts. So now that I have that, I can say the integral of u d omega, which is the integral of v cubed e to the negative m v squared over 2kt dv, is actually equal to u omega minus the integral of omega du. So I can go ahead and write that as u we figured out was v squared, and omega we figured out was kt over m times e to the negative mv squared over kt. Now we're integrating from 0 to infinity, so that's where we have to evaluate the u omega. Now I'm saying minus the integral of omega du. We found out already that omega is kt over m times e. And by the way, I still have the omega, which is kt over m, times the dv, which would be 2v e to the negative mv squared over 2kt dv. Now I need to separate this work here, so I'm just going to draw this line around it. Okay, so that's what our integral is. I think you can tell that if we evaluate this first term, the v squared times parentheses, this stuff, if we evaluate that at infinity, you can see e to the negative v squared as v approaches infinity is clearly going to get way smaller than v squared going to infinity. So that part's going to be 0. And then when we substitute in the 0, we're also going to get 0. So this portion right here just turns out to be 0. So right here we have 0. And I'm left with now, I know we don't have much time, but I'm left with now negative 2kt over m times the integral of v e to the negative mv squared over 2kt dv. And again, I'm going to say let u equal mv squared over 2kt implies du is equal to mv over kt times dv. So now I can replace the dv with kt over mv. So when I do that, I'm going to get negative 2kt over m that was already there. Now I'm going to get kt over mv. Oh, excuse me, that v is going to cancel out with the v inside the square root. And we're going to get the integral of e to the negative u du, which is just e to the negative u. So now I have 2k squared t squared over m squared times e to the negative mv squared over 2kt. Now that is a nasty mess, but hopefully y'all can all follow it. Now all I have to do is put this back in the original expression, which we have right next to the letter A. So I'm going to go ahead and switch up colors too, just to make it a little clearer. So now I'm going to say V bar is equal to 4 pi. Ooh, something I forgot. I can't believe I didn't write this. Everybody change this up here. Both of those cases you got to divide by n. Everything else is right. So in this case, V bar is supposed to be all this over n. So that 4 pi is just going to be 4 pi, not 4 pi n. Now I have m. Oops, I need blue still. Now I have m over 2 pi kt to the 3 halves, plus I have negative 2 k squared t squared over m squared times e to the negative mv squared over 2kt evaluated from 0 to infinity. Now this is actually, it looks really messy, but I'm going to treat the 4 as 2 to the 2. The pi is going to be raised to the 1 power, which I'm going to call 2 halves, minus the 3 halves power, because that's in the bottom, and that's the only other value of t. The k is going to be on the top as 2, but we're going to call that 4 over 2, minus 3 halves. And the t is going to be 4 halves, because it's 2 again, minus 3 halves, like that. And finally, I've got an m that's going to be to the negative 2 plus 3 halves. Now I seem to have gotten everything. All my 2's. Oop, I have a 2 to the 2 plus 1. So that's a 2 plus 1 there. Oops. Okay. And then when I evaluate this at infinity, you see that as this approaches infinity, I get 0. But when I set it equal v equal to 0, I get 1. So this is 0 minus 1 here, which is going to get rid of the negative that I had. I've actually dropped it anyways by mistake. So there it is. But that's going to get rid of that negative. And now let's steal this and go over to the other page. Hope I can fit it in. So I'm going to copy that and I'm going to paste it right here. Now, if you guys got to go, you're welcome to go ahead and leave. I know we're about up right at the mark. So I completely understand if you have to leave. I'm going to finish the other part of this example and then I'm going to close it up, but it'll be on the video. So you guys are welcome to leave. Make sure you chat me your first and last name if you haven't already. I'm going to go ahead and finish this out. So now I have V bar is equal to, the negatives cancel out, and that means this and this become positive. 2 is going to be 2 to the 3 power, so that's an 8 basically. So I'm going to have, was that it? Then I have a 2 somewhere else. Had a 2 there. Yeah, that all looks okay. Uh, in actuality, let me double check and make sure I got the same result. Yeah, so this is just 2 to the 3 power because I had 2 to the 2 power for the 4, and then I had a 2 to the 1 power. So that's 2 to the 2 plus 1 is 2 to the 3, which is 8. And I don't know why it's red now. That's 8. Now I also have pi, which is 2 halves minus 3 halves. That's negative 1 half. Like that. So that takes care of this one and this one. And now I have k to the 4 halves minus 3 halves. That's k to the negative 1 half. That takes care of that one. And I have t to the 4 halves minus 3 halves. So that's t to the 1 half. That took care of that. And I have m to the negative 4 halves. Since it was actually negative 2, it should be negative 4 halves. I don't know why I didn't write it there, but negative 4 halves plus 3 halves. So 3 halves minus 4 halves is negative 1 half. And that, of course, gives me m to the negative 1 half. And that's basically it. So I can say the velocity is, and I think this 8 is an error. I don't know where the 4 went or came from, but anyways, I got this times kt. T is in the top, m is in the bottom. So this would be pi is in the bottom. Oh, that's what it is. It's 8 over pi is what it turns out to be. I dropped something somewhere, but the result is 8 over pi kt over m, which your book has given you as the average velocity. The square root of 8 over pi, my calculator's all of a sudden being a jerk. I don't know why. Won't let me just clear it. So anyways, I guess I'll do it this way. 8 divided by 3. So that's 3.89, which oddly enough is the same number I got just a second ago. That's 3.89 times the square root of kt over m. So that's how that one worked. Again, something's wrong with the 2. This 2 was supposed to come out to the 3 halves, but I don't know why I don't have that. Oh, I see why. I completely missed the 2 in the bottom of the 3 halves power, so that's what happened. Okay, so keep that in mind. Anyways, that's roughly how you do it. For part B, what we want to take is df over dv and set it equal to 0. Well, the f is, we're going to say d by dv of 4 pi n times m over 2 pi kt to the 3 halves times v squared, times v squared e to the negative mv squared over 2kt. So that's what we're supposed to take the derivative of. I think you can see that these constants out in front, they're irrelevant since I'm setting all this equal to 0. So really all I got to focus on is the derivative of what's to the right of that, which is the v squared. So I'm going to get outside 4 pi n times m over 2 pi kt to the 3 halves. And that's supposed to be irrelevant. But now I'm going to take the derivative of the v squared part because this is a product rule. So it's going to be 2v. That's the derivative of the first term. Now I'm just supposed to multiply this by the second factor. And I said term, I meant factor. Now the product rule says you take the derivative of the first one and multiply it by the second factor. Now you take and add that to the first term or the first factor times the derivative of the second factor. So that's going to be v squared is the first factor, and the derivative of e to the negative mv squared over kt is negative mv over kt times e to the negative mv squared over kt. Remember when I took the derivative of v squared, that gave me the 2 that canceled out the other 2 in the bottom. Now setting all that equal to 0, you can see again that this e is not going to play any role in this. So all I have now is 2v minus mv cubed over kt is equal to 0. So we can divide both sides by v and leave a 2 there and a nothing there. And lo and behold, we're going to get v. We're going to get v is equal to 2kt over m, and then we take the square root of that, and that's the actual answer, which is approximately 1.41 times the square root of kt over m. So in general, what we found was v RMS is equal to the square root of 3kt over m, which is also about 1.73 times the square root of kt over m. We found v bar is equal to the square root of 8 over pi kt over m. Remember, I figured that out. I had left off the 2 to the negative 3 halves power, and that would actually fix it so that we end up getting 2 to the third 3 halves power in the numerator, and the 3 halves means 2 cubed, which is 8, under a square root. So that's where the 8 came from. But this turns out to be 3.89 times the square root of kt over m. And then the most probable velocity, Vp, is the square root of 2kt over m, which is 1.41 times the square root of kt over m. And the Boltzmann distribution, for the record, actually looks like sort of like this. It goes up really sharp, and then it goes down like that. And your book made a point to say that only 1% of the molecules have a velocity more than 4 times the average velocity. So this little n down here is a very small part, but the big thing is the peak. That's V most probable, which is about 1.41. The V average is about 3.89, so that's much bigger, and that would be roughly here. That's V bar. And then the V root mean square is right in between the two, like that. And that is a plot of velocity versus temperature. Anybody have any questions? Actually, that's f of v, I should say. Any questions? Actually, it's f of v versus v. I did make a careless mistake there. That's not supposed to be v, t. That's supposed to be v. So, it looks like I got two students left. Michelle or Alex, y'all have anything?
So I actually am in the 241 night class.
Mm-hmm.
So I don't know if Alex had anything first, because I have
Okay.
like a question from that course.
Okay, Alex, did you have a question? She's here for an office hour, so
Oh,
you get first
she can
dibs.
go first. I have multiple questions, so it'll probably take longer.
Okay, go for it, Michelle.
So I am getting stuck on the questions that are like where you are looking for like common knowledge, I guess.
Mm-hmm.
And so like for instance, I had one on the homework that was the Pentagon floor area and how many people can stand side by side.
Oh, gotcha.
And I I found two measurement like I think I'm an overthinker and that's the problem with it is like
Mm-hmm.
I'm like I can see too many variables.
Did they
So
give
I
you
kept
the square footage of that one, or they want you to estimate that too?
no they want you to I guess look it up because I was Google searching it and it's supposed to be 6.5 um or I'm sorry, 6,500,000 square feet. But
Mm-hmm.
then there's a separate thing online that said like the office square footage is like a 3 million something.
Yeah, so that's
And
Jim
so,
cutting out the hallways and stuff like that.
right, in like the courtyard or whatever. And so I tried calculating it both ways and I kept getting the answer wrong on Pearson. And so I don't know what I'm doing wrong because
Well, what did you? Go ahead. What did you do? You divided what by
I
what?
divided the total floor area by the average area per person.
And what'd you
Uh,
say? What'd you estimate that to be?
I had it at 3.25 times 10 to the seventh.
Oh, but what did you estimate for this area of a human?
2 square
Or
feet.
okay, so that's a figure they gave you, or is that what you guessed?
No, that's just what I'm guessing. And like that, I think that's where I'm struggling is like they're not giving the figures to like
Hmm.
so I got stuck on two other ones. Like one of them I got right, but the other one was about the average number of heartbeats or yeah, beats per lifetime.
Right.
And I calculated all the things out and it was wrong. And I'm like, what is the average then that they want it to be?
Okay.
Like what
Now the
beats are they going with? Or, they
two
don't give
feet
you that.
doesn't sound bad to me. I think that's pretty close.
Yeah, it's like
But
crowded, but it's
yeah,
not.
yeah. But did you remember to convert the feet to whatever units the footage of the? I mean, I think you gave me the square footage in square feet, right? For
Yes, it
the
was square
okay,
feet and square feet, and
okay, so
then
that's
it
right.
would be total people. So it wouldn't like change, that.
Yeah, you should be roughly 6.5 million divided by 2. So that's
Yeah,
what
0.25.
3.5 times 10 to the 6 people could
Yeah,
fit in it. So
yeah.
in that case, you'd call it 4 million or 4 times 10 to the 6. So you only want one sig fig. And did you try 4 million and it didn't work?
I don't know that I tried four. I think I did 3.2.
Yeah, that could be the issue, but let me just look at the problems to see if there's something that I can tell you to help you. So I'm going to
Okay.
pull up
Yeah, I
the
was definitely like I wish there were like variables at least like given just so that you're not guessing because I don't think I'm guessing correctly. Like
yeah. Well, it sounds like you did everything right, so I wouldn't worry much about making that any better. Remember, what I try to tell my students is uh, there's actually a lot of errors in the online homework system. So sometimes shooting
uh,
for 100 literally makes you learn physics incorrectly because you've got to sometimes get a wrong
oh,
answer. So I
okay.
just focus on you using as learning and just know keep your average, 75 or higher bare minimum. And
Okay.
at the end of the semester, if your grade's really dogging you, talk to me. There's a way I have that I'll let my students improve their score. Do you
Okay.
remember what number
Okay.
problem that was? I'm looking at it right now.
Ooh.
Compression of Jaguar air bubble.
Um I
Maybe it's the first or
I
second
didn't
one.
write down the I think it might have been like somewhere in the mid. All right, hold on. Let's get that question two.
Okay, 1727
So
is
maybe
not.
like three or four, because they had it was four parts, I believe, of
Uh-huh.
this section. Um, order of magnitude that it was it's that those problems.
Gotcha. I'm looking, I just did 1740, 1743. Let me look at that. Oxygen, no, that's not it. 1755.
I don't think we had anything about oxygen.
This was chapter
Uh,
17, right? Oh no, I remember why.
no.
Darn it, you're in chapter 1.
Yeah,
I'm
yeah, yeah,
looking at
yeah.
my homework.
I was like, wait a second, I don't remember oxygen,
Yeah, I'm
but
in the
maybe
242 class, so I was thinking it was that.
like
That's not gonna help me.
I was like, I thought this was the only parts I missed, but maybe I missed something else.
No, no, you did fine. Let's see if I can get there now. I'm trying to look for the actual problem so that I can then find a what they're using and see what you missed. That's usually the
Okay.
easiest way to do it.
Yeah, because I
So
don't know if the
241.
sig fig thing or not sig fig. I'm sorry, like if I'm not using the correct exponent or something, or
Right. Yeah, there is a danger. Sometimes students make a mistake in trying to put in scientific notation, so that sometimes will lead you consistently off by a factor of 10. Made to order of magnitude.
I wonder if
Okay,
that's
how many people can fit into the Pentagon? Okay, let's see. The hints it gave you are what information should you be looking for? What building in the world has the largest floor area? So how many people can fit in the Pentagon, which is once the largest office building in the world? Assume that everybody must be standing on the floor. What they use, round to the nearest power of 10, then express your answer as order of magnitude. For instance, if your estimated is 3 times 10 to the fifth, enter 5. Okay, so they're just wanting you to enter the exponent, evidently. So
oh
yeah, if you just type in the 6 is what you should get because you got 3.5 times 10 to the sixth or 3 point whatever times 10 to the
oh
sixth.
my
Just put the
gosh.
6 in.
So I
So
was
that's
putting the
all it
whole
was.
answer and not okay.
Yep. So
So
you
I
did it
wonder if
right.
that's what I'm doing with the okay, so average beats the average heart or beats I'm sorry, for a lifetime. I
Mm-hmm.
had gotten 3.2 times 10 to the ninth,
Mm-hmm.
but and that was after doing like an average of 80 beats per minute or yeah, 80 beats per minute times a day's worth of minutes, so 1440. And then I got 1,100 I'm sorry, no, 115,200 beats per day. And then I multiplied that by the average number of days of a lifetime. And then that's how I got like the 3.2 times 9 to, or sorry, times 10 to the ninth. So am I doing something wrong with the exponent?
No, and this is another one for that part. They're expecting you to put in 9 because that's the power of 10 that you
Ah,
did.
okay. Okay, so I'm making dumb mistakes.
Yeah, it's
Okay.
big bold print. It says it across the top. For instance, if your
Ah,
estimated answer is 3 times 10 to the fifth, enter 5.
or,
So you're just supposed to
okay.
enter 9, and that is exactly the right answer. So you did it right.
Okay. All right. And then with the I think with the last one, I think that that one was I
You
was
buy a
having more
can of soda. About how
difficulty.
many molecules from that famous bathtub of Archimedes are there in the can?
Yeah, I don't even know where to start with that because I was like, this is like very hard for my brain to wrap around, I guess.
Right. So what you do is you estimate the number of molecules in the bathtub for Archimedes, and then
Right.
you realize that those molecules just get up into our atmosphere and ultimately come down into our water sources, and therefore that fraction, if you take the number of molecules that Avogadro's bathtub had in it, divided by the total number of water molecules on planet Earth, that's the fraction of all molecules that came from that bathtub. So if you now multiply that
Oh, okay.
fraction
Okay.
times the number of molecules in the drink, then you'll have the number of molecules that were part of Archimedes. And again, they're wanting just the exponent there.
Okay. Okay. I need to note that because wow. Okay. All right. That helps a lot. Thank you so much.
No problem. Yeah, that's a very neat problem, but you're going to be surprised how many molecules of Archimedes' bathtub are in our drink. So
Yeah, it's kind of gross.
yeah. That's the whole thing about homeopathy too. So
Yeah, yeah.
if
Okay.
the if the water remembers whatever chemicals you had in it in the past and now you've diluted it 10 times, then guess what? The same thing's going to happen with poop that someone puts in the ocean too. So
Oh,
yay.
yeah. Yeah. Oh, yeah, that's interesting.
All right.
Oh,
Anything else, Michelle?
nope, that's all I had. Thank you so much.
All right, no problem. Have a good one.
You too. Thanks. Bye.
You're welcome. Alex, you have a question now, bud?
Hi. I have a couple questions. I'll try to ask you the questions that will hopefully be shorter first.
Mm-hmm.
I'm looking at the practice test right now, and it says the
Correct.
practice test face to face, chapter 17 to 20 is due tomorrow. Is that true?
That shouldn't be the 21st. I thought I made that a little later. Let me check my syllabus though, but as a rule of thumb, no, it should not be tomorrow. So
Okay.
no matter what, anybody sees this video, no, it's not tomorrow. But yeah, I'm going to check my syllabus real quick just to see.
I'm pretty sure in the syllabus it's correct. Is on the canvas itself. It shows
Okay,
as the
gotcha.
21st.
Yeah, the first online test is not due till February 2nd. So
Um,
that should
okay.
make it a little easier on you. That being said, let me go ahead and go to the modules and correct that. I thought I'd already changed those dates, but I might have missed one or accidentally undid it after I did it. That's always a exciting thing that happens to us old people. Online tests. Yeah, when I'm looking at your class, the 242 online, it says online test one was supposed to be due December 21st. But that was last year. So now I'm going to change that to February 2nd. Okay, so now that's set up properly. Anything else on that one, Alex, or anything else otherwise?
So with my physics lab, I was supposed to take it tonight, but it was
Mhm.
canceled, and it's based off of, or the topic was electric fields and
Mapping.
uh no, it's like equal potentials.
Oh, yeah,
Yeah,
equipotential lines. Yeah.
but I don't know if we're going to be able to redo this lab or ever take it again. So I was just going to ask you kind of like what type of lab or how would that lab
Okay, so the
work?
way that lab worked was we take something called a galvanometer. A galvanometer is sort of like the simplest version of any kind of electricity meter that you could use. It's technically an amp meter, meaning it measures amperage. But what happens is you have one terminal for the amperage or the current to come in, and then it wraps around the bar magnet, and then that wire continues to another terminal for it to come out of. Now that bar magnet that it's actually wrapped around is attached to a needle that points straight up. And the reason why it points straight up is it doesn't have any more affinity that the magnet that the wire is wrapped around has no more affinity for the magnet on its right than it does for the magnet on its left. But when current starts to go through it, that makes that magnet stronger and gives it a very specific polarity so that it either attracts to the magnet on the right, which would read a positive amount of current, or it attracts to the one on the left, which would read a negative amount of current. And in both cases, it gives you the magnitude of the current and it tells you what way it's going, either in the left port or out the right port. Now, what we do with that device is we take and connect one of the terminals of that device to a particular part on carbon paper, and that carbon paper has like some metal terminals on it. So like the shape of a parallel plate capacitor would be a piece of metal and a piece of metal that are fairly close to each other. So if you connect to this, then you look at all these spots in between the two pieces of metal. Everywhere that has a reading of zero has exactly the same electric potential, which is like potential energy, and therefore has what we call the same voltage. So what you'll do is find a bunch of dots that all read zero, and then you sort of connect those dots with a smooth curve, and that's one line of equal potential. It's just like if you've ever seen a topo map they have those circles and stuff on the topo map. Those circles represent the place where the altitude is exactly the same. So everywhere on one of those circles has exactly the same altitude above sea level. If you go to a bigger circle, then that's a little lower. If you go to a bigger circle still, that'll be lower again. But that's what you're going to do is you're going to get these individual lines in between the two metal plates, and that's sort of like where you could put a charge, and all everywhere on that line it would be compelled to move to the right or left and have a certain specific speed when it gets there. Now, then you'll have another line, and that will represent a different speed when it gets there, and another line will represent a different speed. So by doing that, you can find out where the voltage is sort of the same in between the plates, and then just like the fastest way down the hill is going perpendicular to those lines on the topo map, the fastest way to go for a particle is basically along the electric field lines, which are perpendicular to those metal surfaces. So perpendicular here and perpendicular here. And then it hits each one of those equal potential lines perpendicular. So it's just a way, and it's really the only lab where we actually get to measure and see, in some sense, the electric field. So that's what that lab is. If you look, you can you'll find it on my YouTube channel. I did a intro to that last semester, or it might have been the semester before last. Just do a search for the name of that lab on my YouTube channel, and you'll find me introducing it to you.
Cool. Yeah,
It
no,
might
I'll
be a lot.
definitely give that a shot.
Yeah, it'll definitely be a little clearer than the explanation I gave you because I really need all the equipment here to show you and then show you some graphs. And I do a little bit more of that in the description.
I think I understand it where we first measure the amperage
Hmm.
of whatever currents going through the whatever currents going through the equipment, and
Right.
then but
This, I'm
the
drawing this
magnet
for
is
you
throwing me off
now.
just a little bit though.
Go
Okay.
ahead. Yeah, so this, I just forgot. I can just draw this at least to be helpful. So we go up here, and this is literally what one of the sheets of paper look like. It's carbon paper, so it's sort of conductive, but not that conductive. But basically, it's got these pieces of metal shaped like this black thing I see here, and everything else is just carbon paper. So not only that, the carbon paper has very specific dots like graph paper. So here's a dot, here's a dot, here's a dot, all these little crosses on this graph paper that you see can be thought of as dots. So what you're going to do is you're going to take this galvanometer, which has a terminal right here and a terminal right here, and it's got a window right here, and that window is where you read the actual current going through it. And it's a small amount of current that this galvanometer reads, but normally when you don't have any current going through it, it's just a red needle going up. And that's what zero corresponds to. So what you're going to do is you'll take a wire, let's say this green wire right here, and you'll attach it to this particular dot in general. Okay. And now you're going to take this particular terminal and you're going to try to find all the places where it reads zero. So this is one, 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 this is one. And you'll get something like that. And then you'll draw a line of best fit for this. And what that means is all of the points on that red line I just drew had 0 volt, zero current going through it. So that means they're all at the same voltage. And if any particle left from there and ran into the plate on the right, it would have exactly the same speed as any other particle that left from that line. Now, if you take that green one and instead go to another dot, let's say right here, then you're going to get another series of spots, and that one will have a different voltage as well. And this will be represented by this kind of line. And you keep doing that, and you get basically lines like this. Those are all equal potential lines. This one might be 2 volts. This one might be 1.5 volts. This one might be 1.0 volts. This one might be 0.5, and this one might be 0.2, right? Now, the electric field lines, by definition, have to be perpendicular to all equal potential surfaces. So right here, I draw a line perpendicular, and then it's got to hit this, and that's got to be perpendicular, and it's got to be perpendicular to this one, and it's got to be perpendicular to this one, and it's got to be perpendicular to this one, and it's got to be perpendicular to this one, and it's got to be perpendicular to this one. So what we'd end up getting is a line this way. And if we consider this the negative terminal and this the positive terminal, then the direction of the electric field is that purple arrow. And you can see that that purple arrow is going to be the same over here because all these lines are essentially parallel, at least until you get to the edge. When you get to the edge, it's going to start to do a little bit like this and maybe even a little more like this. But that's what you get to do in this lab is you get to determine those electric field lines from the green and red lines that we found by finding the places where the voltage was or where the current was zero. Does that make sense?
I do believe that makes sense. I haven't learned anything about the electric field yet, so
Yeah, that's sort of the bummer about this where I go over thermo first. You jump into electricity and magnetism in lab before you do the electricity and magnetism in lecture. That's a good thing to do by itself in some cases, but sometimes it's better to do the other way. But you have to do, I think my class, I normally make them do at least 3, but sometimes other instructors make them do at least 5. But this is another shape you'd do, and you'd get the electric field lines going like this. But they all come from first finding those lines of equal potential, which would be something like this, and then it starts to curve like that. So you'd first do those vertical lines with the to find the equal potential, and then you do those arrows to find the electric field. Any questions on that? Hopefully that'll help you a little bit.
I think it does. So just to ask, when would we go over electromagnetism?
We start that in chapter 21. So
Okay,
we do 17, 18, 19, 20, and then we start electricity and magnetism.
very cool. Thank you so much for your help.
No problem.
All right.
Is that
Have a good
sufficient? You
night.
need anything else? All right. You have a good one, Alex. Take care, bud.
Yeah, no, it's all good. All right. See you Thursday.
See ya.